Hello everyone. Welcome to the WISE Zoominars. So I'm Qingxiang Liu from Ocean University of China. Today I'm very glad to introduce our keynote speaker, Dr. Jean Bidlot from ECMWF. John has working in ECMWF, I think, since the 1990s, and he works on the development of the spectral wave model of ECMWF Earth system model and the forecasting system. He has also done extensive research in the role of wind waves on the atmosphere and on the oceans. Today, John is going to talk about the brand new ERA6 wave reanalysis datasets they are going to produce soon. But before we start, I also would like to remind you guys that the next WISE meeting will be will be held in Venice, Italy, in next May. And the abstract submission deadline is 21st December. So if you are interested in this meeting, please submit your abstract. And you can also find more details at this website. Okay, John, so it's all yours. Thank you.
Thank you.
I will stop share. Okay.
You confirm that you see the presentation?
Yes. Yes, we can see. Thank you.
All right. Good afternoon, everyone. Yes, I'm Jean Bidlot, and I'm gonna talk to you about the upcoming reanalysis ERA6 that ECMWF will start produce soon. It's high time that we start soon. And as you know, ECMWF has been in the business of producing reanalysis for quite a while. The current one, ERA5, like highlighted by this box, is still in production and widely used. And we hope to essentially improve on what ERA5 has been doing. And a bit of an outline, so a quick reminder of what ERA5 has achieved and what you can expect then from the next ERA6. I will focus mostly, because there's a wave discussion, on the wave component in ERA6. I will sadly have to mention that in ERA5, the use of altimeter data, part of the data assimilation system, was suboptimal. Lesson learned, we hope to do much better with ERA6 and ingest even more data. Then from early experimentation, I will show you the type of gain we expect with ERA6 and summary and a bit of discussion to some work that may still be able to do in the coming few months. So, as you know, ERA5 is a global reanalysis for atmosphere and waves. There's a tremendous amount of users, a huge amount of data available, and many citation. There hasn't been an economical impact that its value is estimated about benefit of about €1 billion. It's highly used to produce timely climate information, like highlights of the climate of previous years and season. So this is just a little animation showing an intense storm that happened early 1941, affecting the Iberian Peninsula quite severely. And not least, it has been used in recent years for many data-driven applications, so AI and the likes, and been shown to be a very reliable source of information to derive these type of data-driven models. What's the upcoming ERA6? So essentially, we will hope to produce a new reanalysis of 75 years of reanalysis, and it's based on about 8 years of research and development at ECMWF. As you know, ECMWF is primarily a forecasting center. So we aim to improve our forecast, but in doing so, we also need to improve how we digest all the amount of observations that we get from satellite in situ observation and the like, and how we generate this initial condition. Using the same tools, we can then rerun things from the past and reproduce all these analyses And actually, we also do the forecast corresponding to the analysis. So it's called reanalysis because it's things from the past, but they will be run up to real time because we have users that like to use reanalysis data in in near time application. The resolution will go to what we can afford. Ideally, we would like something as fine as possible. So it'll be 14 kilometers. This will be quite an increase with respect to the 31 kilometer ERA5 is. And definitely for the wave, we had 40 kilometers in ERA5. In the new system, the wave model runs on the same resolution, actually on the same grid as the atmospheric. So we'll run at 14 kilometers. There also be, because some application require uncertainty estimate based on an ensemble-based system, with 11 member at about half that resolution for cost reason. Science, as I say, it's 8 years of development, but a new features in this reanalysis is that part of the analysis will be coupled to our latest implementation of the NEMO 4 ocean model, and it'll be coupled in the trajectory. I will explain a bit later what it means in the next slide. But as I say, reanalysis is about combining a model with observation. There's a lot of effort has been driven to try to reprocess observation data rescued from the past to get as much observation from the past as possible. For the wave, it means we will leverage heavily on the ESA C-State CCI, so it's a European Space Agency effort to reprocess and past altimeter and also SAR mission to produce a consistent data set, and we've made use of the data. New products will be before we didn't have ocean parameters associated to the reanalysis. Now we'll have it. For wind energy, we will produce directly different height level for all atmospheric variable. There'll be hourly output as before, and as in ERA5, 2D wave spectra will be again be available at all grid points of the model. We'll produce also daily and monthly pre-calculated statistic. The core output will be in GRIP2, but obviously you can always convert GRIP2 to NetCDF. So what do I mean when the ocean now is part of the analysis system? So in this little cartoon here on your left, you have what we currently do in ERA5 and actually also in our operational system. So we have a couple system that combines land, atmosphere, ocean. Then we do a 4D VAR, so it's a four-dimensional variational data assimilation system for the atmosphere. Within this, the wave model is embedded using a simple OI optimal interpolation scheme. But we do prescribe SST and CIS concentration in the system, so it's kept constant and not evolving during the system. We move into a system because the 4D VAR system essentially is a system in which you run your forecast system, so your whole model, your whole fully coupled system, in which we can add the ocean model and the evolving sea ice model. And then you can put this in when you evolve your system and try to fit it to observation. It is not a fully coupled system, so the 4D VAR is not done on the ocean. The ocean analysis is the initial condition for this system still comes from our ocean reanalysis, ERA6, that has been produced in recent months. The impact is that we create system, especially near the surface, when you bring the ocean into it, any variable that are sensitive to what's happening near the ocean, like waves, but also wind, and so are more consistent. And the impact has been shown that is quite beneficial. Also, you have an evolving sea surface temperature and sea ice, or the sea ice cover, for example, that is evolving on hourly time frame, and for certain application this is quite useful. And this is just a diagram on your graph. The vertical line, if you are to the left of it, indicates an improvement, and a large improvement is with respect to some altimeter data. So it means the altimeter data there's an improvement with respect to altimeter data before you actually use them in your system. So it means your model is already much better. There's still a need for assimilation to improve your system, but at least you have a system that is closer to what the observation is telling you. So this is a schematic diagram, a very simple diagram that represents where the wave model, because we're in the wave model talk here, sits. So in our system, we have an atmospheric system and we have an ocean model, NEMO 4, and sea ice cube that is associated with NEMO 4. And in there, the wave model, EC1, as we call it, is part of the agent that exchange information between the ocean and the atmosphere. And so, you know, I don't necessarily want to find details of the system as a talk by itself, but in red, I want to highlight some of the key features. So it's 14 kilometers for both atmosphere and wave model. We will also activate what has been in the plan for so many years, but never done it. No, we get currents from the NEMO system that it can be given to the evolution of the spectrum in the wave model. And as I mentioned, this is also run as part of the 4DOR system. I'm a bit sorry here for people who know that in recent time we spent a lot of work trying to improve a wave in CIs. This development was slightly too late to be included in the system. It'll be included in our next operational system that will actually become operational within a few months next year. Now, ERA6 is not really something that you will judge on the quality of the forecast, but we still do this because we're so used to producing forecasts. So if you were to run forecasts from the past, from ERA5, with the ERA5 model, and from ERA6 with the ERA6 model, and you compile some forecast scores, so how good your forecast is respect to different set of observation and your actual analysis, you will see that the plots both on the bottom left here on the right is mostly blue, which indicates for many variables across many forecast range, there's a significant improvement. Or if you're not convinced, the classical way to look is this plot, this curve is anomaly correlation on the top. The closer to one, the better. And you see that the ERA6 is the black curves here is about 12 hours better than the ERA5. So this is quite a substantial improvement. All this is to highlight that we have a much better system, let it be in analysis, but also in forecast. Now, specific wave model development, they will go into ERA6. Obviously, these are some features that are already in our operational system or about to be made operational, but they are different from what ERA5 has been using, because ERA5, as I say, is quite an old system. Over the years, that's where a lot of my work has been spent, is we've tried to better control how we specify the momentum transfer under strong winds, essentially to try to produce the strong storm as well as possible, and in particular hurricane and tropical cyclones. So the few changes that went since ERA5, or, you know, in chronological order, it was a cap on maximum steepness is something we put in our system that had a net effect to also reduce the drag coefficient for high wind, which was a good thing at the time, but it was not enough. And so we leverage into the Ardon physics package for the people more keen to WaveWatch 3. This is a so-called ST4 package that, when implemented, was quite beneficial to the coupling as we have it implemented, because in there's an implicit representation of wave sheltering to the sheltering factor, and that had again a nice impact on controlling the amount of momentum, atmosphere, and waves exchange. Then in 47R1, we had a quick fix when we realized, and I will explain a bit more in the coming slide, how the Charnock and the very strong wind needed to be reduced. And 49R1, which has been operational for about a year now in our operational system, I work closely with Peter Janssen to extend his physical representation of wind input to include effect due to small waves, the gravity capillary waves. So these are the small waves that are not really represented by the wave model, but with the effect that it controls quite strongly the exchange of momentum. And also we introduce a nonlinear feedback on the growth rate, which acts in the same way and behaves in the same way as this ad hoc sheltering coefficient that the ST4Physics has implemented. We also included effect of heat and moisture, C-state dependency on heat and moisture flux. So the waves are contributing and enhancing transfer of heat and moisture under high wind, therefore strong waves. So, zooming at exactly what I was trying to talk in shorts is that we have an atmospheric model, we have a wave model. Every time step you get new wind. The wave model generates waves, obviously, but in return, it also is able to determine how much momentum is being extracted from this wind and return this information in term of a Charnock coefficient, because in atmospheric model, quite often, the roughness length scale that appear in the representation of the wind here on your left, this is how logarithmic wind profile is. For now, just forget about the stability correction for the explanation. And then you need to specify this roughness length scale, and then it's usually done via a Charnock relation with a coefficient here that has C-state dependent. That's what the wave model is representing, is this change in the Charnock. So before 47R1, you see we had this type of stress. Notice that this is a density plot, so most of the points are around here, about 0.18 type of value. But we know that for the high wind, the drag coefficient was found to either saturate or even decrease. And there may be many reasons for that, but one of them is definitely the interaction on wind and waves. So we went through different phases to say, well, we need to reduce it. And first at 47R1, we said, oh, the Charnock parameterization that is represented by the Janssens physics is given by this expression here. Essentially, it's function of this tau W. This tau W is the wave-induced stress, is the amount of momentum that is taken to generate waves. And the larger it is with respect to the total stress, the larger this Charnock is, and therefore strong feedback. But we realized that there was a tuning coefficient that essentially was fixed to a value, but we made it dependent then on the 10-meter winds, with a sharp reduction on the for high wind. This is value about 30 here, so it's when tropical cyclone starts to intensify. The net effect of this is that we were able to represent tropical cyclones or hurricane much better. So in the middle here is a snapshot of a wind field. The redder or pink or purple color, the stronger the wind. This is in the case of Hurricane Laura. If we had not done this, you would see that the plot to your right is less red. Essentially, you have wind that are about 10 meters per second lower. And this is just connected to the fact that in the old system, you had this green curve, which is the drag coefficient in terms of 10-meter wind. And the old parameterization somehow had it increasing ever so much that essentially you were keeping the hurricane way too much under control of the waves, and you had to relax it. So we relaxed it, and then the blue curves then generated a drag coefficient that is more in line with recent observation. By this, you allowed the hurricanes to fully evolve and further deepen, generating much stronger wind, as shown by the middle figure. However, this is something of a solution that was more a fix or a hack that we did it in response to trying to quickly improve our hurricane forecast. But it was not something that we really liked, because it was coded with a threshold on the wind. And, in physics, you may want to represent this threshold a bit better. And so we went back to the original parameterization of the Janssen, where essentially at the core of it assumes that the log profile applies near the surface. So as expressed here by this expression to your left. And as I mentioned, the Z0 then is connected to the momentum flux that is taken from the atmosphere and used to generate waves. So essentially, it's connected to the input source term. If you integrate this and then you multiply by the phase velocity, overall frequency and direction, and it's a kinematic stress, so you divide by the air density, and you multiply by rho, so the water density times g, then you have a momentum flux or stress. And the parameterization of the Janssen's physics connects to the ratio of this wave-induced stress to the total stress. But as I mentioned, there is this ZB, or this alpha time U star squared divided by G, which is fixed. It was fixed to a value. And when it was originally designed many years ago, it was supposed to represent the impact of unresolved short gravity capillary waves, so the bit that the wave model doesn't really explicitly represent. And we fixed it to a value, and it was tuned to fit some growth curve data at the time, and everything seems to be working fine. And once you have this, then the input then is expressed as a growth rate times the spectrum. However, it turns out that this assumption that near the surface the profile is logarithmic is not truly true because of the strong interaction between wind and wave. The wind profile should actually slightly deviate from the log profile. And therefore, if you put this in and you allowed it to slightly deviate, you find at first that your growth rate that you would otherwise obtain with the log profile, this gamma 0, is renormalized by these two quantities that are connected to the actual, these two normalizing factor N1 and N2 that are connected to essentially the input, because growth rate times spectrum is the input, but weighted in a different way. And once you put all in this, you realize that under very strong wave condition, depending on you start to have this renormalization of the growth rates. The stronger the wind, so the black curves are for 15 meters per second, and the red curves is for 50 meters per second, and the solid line is what you will get if this renormalization didn't expect, and then the dashed dot is, you see that the growth rate is slightly less. So essentially, this nonlinear feedback acts into reducing the growth of the wave. So it acts as a cap in a sense. And this allowed us to replace this use of a ad hoc sheltering coefficient that's just a number that you try to cook up with a physical representation. So as the wind is blowing, the waves is developing, and then this sheltering comes into play because the waves are growing non-linearly. Now, the next factor was to find that this roughness length for the unresolved short but gravity waves was actually not, you should not fix it with a single number. And so you need a model, a very simplified model for what's happening for the short wave. And then Peter in the past had worked on a model originally developed for radar backscattering modeling and the VIRS model. And then we implemented this simple model and were able to then determine that this background roughness was no longer fixed by a number, a single number, but varied with wind. But in order to do so, everything is dependent on the total stress, the atmospheric stress. And so the scheme that we had in place is a bit complicated because it has to be iterative. But once you put this iterative into place and do enough iteration, you converge to a solution so that this background roughness number, alpha b now, is shown to vary. And you will see that the green and the red roughly are around a fixed value. These are the normal type of wind. The low wind, you have much larger value, and the low wind, you have much lower value. So again, this then allowed us to control the stress a bit better. As a consequence, with all this model, we ended up then being able to represent the drag coefficient in terms of 10-meter wind with the red curves here rather than the blue. The blue one was this ad hoc hack that we have done using a simple fix on the wind. And there we have now a model that does it, but it was tuned to be slightly higher because that fits better some recent observation of drag coefficient under high wind. And as a consequence, the new system, sorry, I backtrack, you see that there's a reduction of the drag under storm wind conditions, so from 20 to 30 meters per second. As a consequence of a lower drag, you end up getting slightly higher wind. And this tackles an issue that ECMWF has been trying to solve for quite a while, that we tend to reduce slightly too low winds for high wind cases. And so with this system that is now part of ERA6, we will hope that our representation of high wind will be improved. And we know that based on some prototype here in the red are ERA6 prototypes, things we've run over the past year or so. And if you show here, this is the number, this is on the y-axis is cyclone category and the number of cyclones. And you see that there are many more red points here where there's none, where it means that ERA6 is able to generate storm of category 3 and 4. Whereas ERA5 was totally unable to do so. Obviously, it's more than just the wave-wind interaction, it's the whole system, but it's quite encouraging that it's much better. Another way to look at it is here to your right is the minimum pressure in terms of maximum wind, the IB track. So the observation is the red curves, the black curve, the red curve is ERA6, so what we expect ERA6 will be. And you see it's much better than what the ERA5 in the blue is doing. All right, all this was about models, so we are convinced that we have a much better model. Now, what do we do about us using data to improve the reanalysis better? So for waves, we're using altimeter wave height. And so in ERA5, this is what we've used. On the left here, you have the list of the missions that we are currently using in our operational system. And the green line is actually the data that have been used by ERA5. And you would quickly notice that there's a big gap in recent mission, the JSON3 and all the Sentinel. And to be honest, this is all due to a lack of resources. And so some work should have been done to try to maintain ERA5, but it was not done. That's the way life goes. Noting that my new colleague working on this is hoping to reintroduce some of these satellite in what we call ERA5T. So it's the near real-time ERA5. Because ERA5, I want to reassure people, will still go for quite a few years being produced, even in parallel to ERA6, when ERA6 will start to appear. And so lack of data. Another issue is if you look at trying to use ERA5 for any form of trend analysis, and here it's not really a trend, but the thin line are monthly mean of ERA5 globally of mean wave period to your left and significant wave height to your right, and the solid line is the running mean over a year. And you see with time, so it's from the late 70s. You see there's this jump here. And if you know anything about altimeter data of the one we are using, when the ERAS1 first appears, roughly when ERAS1 was first used, there's a jump that doesn't look natural. And indeed, we found that we did not use the ERAS1 and 2 data properly. So another sad phase. And we identified why it was the case, and it was missed. And by the time we discovered it, we couldn't rerun that part of ERA5. So it's a feature of ERA5, sadly. And then I took this, thank you for Guillaume Daudet, who is part of the ESA CCI C-State, the ESA C-State CCI team. And we have different things, but if you focus on the panel, the second from the bottom, is when it compares the different satellite mission that you have here in the different colors here on the legend, and you see they are, and these are monthly mean going through time, and you see there are some jumps happening and some weird feature in the features. If he does the same plot around a WaveWatch 3 like a WaveWatch 3 hindcast, so where no altimeter data have been used, no such jump happened. And I did a quick attempt at trying to match his timeline with the use of our timeline of altimeter data, and you clearly see this one jump is when we went from the ERAS 1 and 2 to using other satellites. So we know this is connected to the wrong use of the early mission like ERAS 1 and 2. And here we also see that it corresponds to cases where we have had issues using recent mission like Saral and us. So without entering in all the mea culpa of who did what, we didn't use the data properly, failed to do quality control as strict as we should have. So some bad data enter the system. We hope to solve this. So how are we going to do this? So, well, thanks to the ESA CCI project, we're able to not use the data we had used for ERA5, but rather use data that has been reprocessed and homogenized as much as possible. So the red lines is currently what we plan to use, if nothing done extra on top of it, from the ESA CCI. As I mentioned, because the system has to run in near real time, and ESA CCI stop after the deliver product. Every so often they can do a new version of it, but they will never run near real time. So we have to connect to the real time data, where on this timeline this is the purple lines, and you see the purple lines will connect to the ESA CCI data. Because I did this work at the time, well, more than a year ago, when we were supposed to have the ERA6 in place and ready to run, I have not benefited yet of some of the latest work the ESA CCI team has done, where they've produced new versions. So you see that I've used mostly version 2 for most mission, and the early mission 1 and 2, I used the version 1. Recently, was made aware that, and they released it, the version 4, and we are hoping not even to reintroduce, potentially introduce in blue here, the TOPEX data that have never been used before in any of our reanalysis, and potentially use better data than the version 1 for ERAS 1 and 2. Sadly, I've run out of time to do anything because this vertical line is 2007. The system is about to be run and enter official production from 2005 on, and so there's no room to really change, or it'd be much harder. I may still look into doing something about that. So in order to try to mitigate as much as possible any surprises with what the altimeter data would produce in ERA6, I said this time I'm going to run the whole data set through our data assimilation system. Obviously, I cannot run ERA6 because that's why we not studied production. It's an expensive system to run because you run the atmosphere, the ocean, and the waves. But you can run a wave model standalone where you force it with prescribed wind. And so that's what we did. We said, okay, let's run the DA system as part of a standalone, so a hindcast. And we estimated also a bias correction of the altimeter with respect to the model. Now, this might be controversial, but we know that when we do data analysis for waves, we may introduce some jump because the data and the model may have a systematic bias. And you might say, well, it's a good thing if the observation says your model is biased. Well, it's this. But if you use this in a analysis system, what the system is going to try to correct this bias, but the model will never really accept it. It's something that is well known in data analysis. You cannot correct biases, systematic biases. The model will never accept it because inside the model, and if we knew exactly why these biases were the reason for this, we would correct for them. The model will always go to what the model does. And so in order to prevent generating any spurious trends in our ERA6 product, because mind you, however back in the past we go, altimeter mission, from the early days of ERA1 is 1991. There may be a few before that, but ERA5 has run from 1945 onwards. ERA6 will do the same. So there's a long period where there's no altimeter data or no wave data for that matter to really be used in our data assimilation system. And then you don't want to have a spurious jump in your trend because you introduce altimeter data. So to do so, we say we're going to estimate bias correction or systematic differences between the altimeter and the model. And sorry, there's an extra message appearing on my screen. And then correct the altimeter. We call it bias correction, but it's more like making the altimeter behaves like the model. Mind you, it's not a huge correction, as you will see. And the hindcasts are based on the same configuration, so the same horizontal resolution, the same model version for the wave model. And the only thing that is a bit of a compromise, I have to use wind forcing for it. I don't have ERA6, so I have to rely on ERA5 wind. We force our system using neutral wind, a surface air density, and wind gustiness. But based on the prototype ERA6, we did a simple correction of the ERA5 wind, so a simple regression type of thing, as shown here. So mostly we correct the high wind, and everybody knows ERA5 winds are not strong enough. So based on this, we have made a statistical correction of the wind, force our hindcast, apply the DA system, estimate what the bias correction should be, and then run the whole system to make sure that there's not a period of data that has not been found where for a few days some data went really weird and so on and so on. We can run this with and result surface currents because now we have our ocean reanalysis product available. So to give you an idea of how it works, on the left here is JSON. So you have a scatter diagram that compare altimeter wave height with model wave height. So the first guess before you do data analysis. And on the right is Sentinel-6. And once you determine your bias correction, you re-estimate, and essentially you find that essentially there's virtually no bias, plus or minus 1 centimeter. And the type of bias here that are plotted, because our bias correction is this term of significant wave height itself. And if I zoom on this for the different mission, you see that, yes, we tend to correct here for high waves. So essentially we correct some features that the model may not represent high value of significant wave height as well as the altimeter. For low value here, we know we probably correct problems that we know for low significant wave height. Altimeter tends to have an overestimation. And in the middle, we probably correct for both. So, the correction is of the order of 10 centimeters. So it's just to guarantee that the trend that people will try to estimate of out of ERA6 will be as real as we can make it. So now we're successful. Again, similar plot where you have monthly mean of mean wave period and significant wave height. The blue curve is what we have if we were not to use any altimeter data. So it's a true hindcast, like the Wave Watch 3 hindcast is just the EC1 hindcast. And then the purple curves here is with data assimilation. And the red one is this one we had with ERA5 when there was an abnormal jump. So I'm pretty confident that that this spurious jump we had in we are in a is as good of a state as we could be. Now, quickly, expected improvement. Because I have all these hindcasts, I can compare to in situ observation, mostly buoy-based observation and some observation from platform in the North Sea or the Gulf of Mexico. And again, the red curve is for ERA5. On your left is the peak wave period from this instrument, and on the right, a significant wave height. And the metrics we use is scatter index, so the standard deviation of the difference normalized by the mean of the observation. The lower, the better. You see continuous curve, and you see the blue, which is the hindcast based on the new system. So as I said, the new model, the new wave model is definitely better than the old ERA5 system. The purple one, actually, I've kept saying purple, but it's actually more pinkish type of curve. It's when you see it's lower than the blue one, so you have an improvement again with respect by using altimeter data. The green one is actually a further improvement, mostly visible for the peak wave period, not so much for the significant wave height. There's a well-known figure is when you add ocean currents into it. And so ERA6 prototype that we've run will have essentially the model, the 49R2 model, the altimeter data assimilation, the ocean currents been activated, and we've run 1 year, more than a year ago, and we produced this purple diamond here, and you see it fits even slightly lower than all these hindcasts, which is a good thing. We recently spun up the system, the actual ERA6 system for 2006 and 2016. So these are generating for you the condition that will be used in very shortly to start the full production of the first chunk of ERA6, sorry. And you see that slightly lower. So it's all good. I think the prototype is working. The assessment of the altimeters shown no big issue with the altimeter data. So we're good to go. And with a few minutes left. All right, so the take-home message is ERA6 is coming and production will start soon. The first spin-up years, 2006 and 2016 has been completed. And why so? Because ERA6 is not run in one single chunk. We have been able to show that if you run it by a chunk of 10 years and you're able to produce a consistent system. The first one is to produce recent data. So we will be running from 2007 for 10 years, and then from 2017 to present time, the first chunk anytime soon. I'm teasing my poor colleagues every time I see him and I say, when are we running? I say, it's coming. So but the end result, all this because of the computer resources allocated to the project. We produce the data through next year, but the release, I'm afraid to say the release won't be until a year after that. So you can expect this first chunk of data to be available by 2027. The take-home measurement is much higher resolution. It has 8 years of improvement. It has an ocean component that is actively acting on both the atmosphere and the waves. You use better use of observation, and for the waves, I'm really hoping that this time we're gonna get it right. It resolve many issues with ERA5. There'll be many more products. As I say, grip2, if you fancy grip2, otherwise convert it to NetCDF. I want to reassure current users of ERA5 near real time, ERA5T, that it will still be maintained for the time being for quite a while. In my last discussion, I already hinted to this, that because of this opportunity, because the production of ERA6 has been delayed a bit. And so on the plot here, you see the other chunk won't be started to be run again in chunks of about 20 years, batch of 10s, until sometime mid next year. We still have a little time to go and see at the ESA CCI version 4, the latest release. I've started working on Topex, so it'd be a nice addition because it's a long set of it's a long mission I'm into, and from what I can see, it's quite consistent, and hopefully we'll be adding the latest version of ERA1 and 2, and obviously it's if time allows, and this is on me to do it, so just push me to do it and it will happen. And thank you for your attention. I hope you found it useful, and I can try to answer any question you might have.
Thank you, John, for this great talk. So, any questions? Oh, we already got a question from Note. So, there's a question. Oh, is there any technical documentation, background errors, correlation lines at all about the OI assimilation over wave height in ERA6 drawing?
No, because you will see that's Bidlot et al. 2016. It will be documented here, but I'm not done writing it. So by the time my colleague and I, but definitely we recognize there's a lack of fine documentation of what is actually being used in ERA5, and this time for ERA6. We'll try to put and describing the OI scheme and the data, the bias correction of the data, the model version use will be in there. I hope this will be out soon.
Okay, John, we have another question. So if I understood well, so the question is waves in ice won't make it to ER6 to start with. Will they be introduced later in the ER6 life cycle, or will we need to wait for ER7?
Sadly, it'd be ERA7 because the science, as they call it, so the model version that went into for ERA6, and if you know anything about ECMWF, is a so-called cycle 49R2, was fixed about a year ago, essentially. There was a few tweaks in there, and everybody else has been trying to squeeze things in, but they were very strict, so no new contribution. In parallel to this 49R2, we've been working on taking this model and work it for the past year into a future version of our operational system. So sadly, we'll have WaveCI's interaction in our operational system. So it's due for implementation sometime in the first quarter of next year, I was told, but not in ERA6. So it'll be in ERA7, I'm afraid.
Okay, John, we got quite a lot of questions, so I will read it again from note. So the next question is from Jie Zhang, working in Harbin Engineer University. So the question is, what's your opinion about computing frequency risks from phase averaged models? Is that a promising direction to work more on?
As far as frequency variables, ERA6 has in it all the latest work from Peter Janssen on the topics, producing an estimate of the single largest wave based on the envelope methods. But we also use two other estimates and based on different parametric fits. So we do have freak wave variables in there, but it's still a phase average model with a spectral representation, and so I think there's still some research that needs to be done for freak waves. But if you do believe that the freak waves is something you can express from the actual distribution in the spectrum and some new breakthrough come in the field, you have all the numbers available. So we will be able to use the ERA6 data to estimate something that may come in the years to come.
Okay, thank you, John. So next question is from Digo. So wait. So the question is, with respect to the influence of waves on the water surface roughness and momentum flux, have you experimented with the approach of, I don't know how to read this name, of weighting the influence of different components of the wave spectrum?
I guess I may have to stop sharing because I don't know which work is referring to.
It's I don't know how to read it.
Let
The
me
pronunciation of this work.
see if I can see the chat. Let's see.
Katov Gross. No, it's a Russian author.
Short answer, no, but it's a good remark. I will need to look into it and talk to with my other wave colleague. Where I'm not saying that anything we do is as a gold standard. I'm always open to look at different way of essentially addressing that we believe waves and atmosphere are tightly coupled. So there's still room for improvement. Yes. Let's see which one I can read them through, or you want to continue reading them?
I can read the question if you want. Yeah. So the next question is from Daniel Hauser. Did you try to assess what is a part of improvement due to better resolution?
Yes, definitely both the wind forcing being better representing the some of the sharp gradient in the wind field, and that has improved middle of the ocean, which say I don't have absolute numbers, but about half the improvement is due to having a higher resolution that with the new physics that sits underneath are able to better represent some of the sharp winds, and the wave just follows. And then the increased resolution in the wave per se is beneficial only really by itself in near shore area, because coastline represented at 40 kilometers or 14 kilometers, you're always winning on that side. But then open ocean is just the atmospheric resolution. And in my introduction, I said, well, if it were me and I had a big deep pocket of money, I will run the ERA6 at operational resolution, but then you might never get the results in the next 2 years. So we had to compromise. So 14 is a good compromise, but it still lacks a bit in doing some of the deepest tropical cyclone, for instance.
Okay, so we have a question from Digo. What's your current hypothesis for the apparent roughening of the water surface for decreasing wind speed? Do you consider Wu's theory of capillary waves effect?
No, most of it comes from a sort of decoupling, and let's call it sheltering. Is just the ability from the waves to take in momentum from the wind is just decreased. That's the main effect that you see.
Okay, so the next question from C. Since there will be an ocean ice component in ERA6, I assume there will be ocean variables like ice thickness, ice velocities, surface currents, temperature, and salinity profiles at a sub-daily resolution, right?
Yes.
Okay. Yes, the answer is yes. Yeah. So the last
And
question
many more,
from
by the way. I don't know them all by
yeah.
heart, but there's a long list of ocean and sea ice variables.
Okay. So the last question from Note. As far as I know, ERA5 has problem with the long-term wave height trend. What's the reason for this? And will the upcoming ERA6 improve on this? Another question is whether ERA5 itself tends to underestimate extreme wind speed. I think you already explained in the
So the
presentation.
trend in the waves, hopefully, it will not be linked to anything linked to using wrong or using wrongly altimeter data. So we're hoping that this will not be present. The underestimation of extreme wind speed, well, it'd be much improved, but I know there are still issues. I mean, that's why even running our operational system still has issues with very high wind, and it's only when you start hitting the resolution that is half the operational resolution, so 4 kilometer global, that you start to be able to represent quite nicely the inner core of hurricanes, for example. So ERA6 will not do that. It be much better than ERA5, but will still fail to represent some of the very high wind in deep tropical cyclones. And the only other also area that we know, and we don't have an answer for it, because if we known that, I think we will fix it. Coastal wind may not be as good as they come, because global model like the one at ECMWF still struggle to do this land-sea transition, especially in semi-enclosed, some of the aspect of the numerics and other aspect, it might be a 14 kilometer grid point spacing for the product, but the actual resolution is usually of the order of 4 times this, so it's still relatively coarse. And then GG, I've been told that I will get another extension for 60 days in a year to work at ECMWF next year. So I'll be able to come to Venice for the WISE meeting, because I'll still be officially doing some work for ECMWF. Well, I'm hoping that I've answered some of your question. In an ideal world, we'll have ERA6 already available. It's quite a bit endeavor from all my colleagues. We have to, there's been a humongous amount of work to produce something that will be much better, and the framework also, because it's more than just the data, is how you will access the data, etc., and the standardization. But hopefully at some point it'll be something that everyone will find useful. If you have any specific question, just please contact me by email or any other means. We'll try to answer as much as I can.
Thank you, Jean.
Okay. Avida.
And you got me on time, which is amazing. Maybe with age, just that to be better.
Okay, thank you, John, very much for this great talk, and thank you everyone for attending this nice meeting. So if you have any problem question, you can send the email to John. And okay, thank you everyone. So we are going to close the meeting now. Bye bye.
All right. Talk to you later.
Thank you, John.